Hello everyone, welcome to Dakshina E classroom program. So here I am going to discuss about one problem. Actually it's based on JEE Advanced 2017 year paper 2. It's passage based question. So let me first read this question. Actually, like many of the student has asked me about this problem because they are not able to understand it clearly. It's finding it difficult. Let me help you in understanding this problem. So let me first read the passage. 1 2L if circular ring of mass capital M and radius capital R near the tip of one's finger as shown in the figure. So if you just look at the diagram, like what exactly is happening in the problem, I think everyone is able to understand that. Like this is the finger and now one person is rotating the finger, and on this like one ring, he is also holding one ring and that ring is also rotating. So that you can see in the diagram, that's what exactly happening here. And then in the process, the finger never loses contact with the inner rim of the ring. The finger traces out the surface of a cone. So the finger, like when it's rotating, the finger is retracing this cone actually. So this cone, like it's like this finger. So you can just imagine this finger is remaining fixed here, but it's like the top point is rotating in a circle. So this is describing a cone, and the radius of cone as shown by the dotted line here. It's like in this diagram actually. The radius of the path traced out by point where the ring and finger is in contact is R. So this radius, like finger and ring both are in contact, and the path of this is a circle of radius small r. So it's mentioned this path is that which is a circle of radius small r. The radius of the in contact, the finger rotate with constant angular velocity omega naught. So the angular velocity of finger is given as omega naught. That is given as omega naught. The rotating ring rolls without slipping on the outside of smaller circle described by the point where the ring and finger is in contact. So here when the person is rotating the finger, actually simultaneously he is holding the ring in this manner. So and the ring, you can just imagine, will be touching the finger at different point here like this when it's rotating like this. So at one point of time the ring will be in this contact in this way, so like it's rotating, that you can see here. So let's say right now at this moment the ring is touching the finger at this point. So finger will be like here, this will be your finger, is it? After some time like finger will be in this orientation. So at this time this is the point of contact of the ring, is it, with the finger, and this ring is rotating and continuously, like here also when finger will be here, ring will be like in this manner. So center will be of the ring will be lying here. Right now center of the ring will be, similarly when finger will be in this orientation, then ring will be in this way. So the center of the ring will be lying somewhere here. So that is what exactly it's happening. What else it's given here? So the rotating ring rolls without slipping on the outside of smaller circle described by the point where the ring and finger is in contact, that you can understand easily. The coefficient of friction between the ring and the finger is mu, and acceleration due to gravity is g. So here you can also understand, like this is like different diagram I have drawn to make you understand what exactly is happening here. So I hope like little bit you're clear with this diagram what exactly it's happening. Another point here, like this point, finger rotating and ring also, they are rotating, they are describing different circles, but we can look at it actually like from 2 points. One way is if you just look at this point, then about this point the ring is actually just see it actually when we are like looking at this point. So just for a moment, what is happening here, this point is at momentary rest, or this is the instantaneous axis of rotation when this ring is actually moving, is it? But if you just focus on this, then it will appear that ring is in this direction. It's like exactly in this way, it's rotating like this, means about instantaneous axis of rotation. It appears the center of mass of the ring is doing purely rotational motion, is it? But here because the point is continuously changing, so it is also actually moving. But if you look at this motion about this point, then it will be a purely rotational motion of this ring about this, and we call that instantaneous axis of rotation. So instantaneous axis, you know the definition, it is the point about which the combined motion of the system appear like purely rotational motion. So exactly in same manner here, this point is lying outside the ring and this point will be actually inside the ring, but the situation is exactly similar, and it's even, I think, like it should be even easier to understand, easier to imagine that yes, here what will happen, actually the center of mass of the ring will be describing a circle at this moment. If you just see after some time, then it will be like this point will be in contact here and your ring will be in describing in this orientation. So you can see just the center of the center of mass of ring is rotating like this, is it? It's coming, changing the point of contact from here to there. So this point can be taken as that is equal to the instantaneous axis of rotation of the ring. Then about this, if the center of mass of the ring is rotating with angular speed omega, the velocity of center of mass of the ring is v, then I can write here v is equal to omega r, where omega is the angular velocity of ring about instantaneous axis of rotation. One way we can understand this way. Another point is simultaneously you can see here actually this center of ring is describing a circle, or it's moving in a circle about this axis also. When ring is, it's rotating like this way, ring will be rotating and the center of ring will be moving in a circle. And so here you can easily imagine, actually, like we can find it also. Look at this diagram from top view. If you look at this diagram, it will appear like this. So if let's say the small circle is this, the in some time from here to there, when it is moving, the angle described by the small circle is theta, then you can see this center will be moving from here to there, and that is also theta. So I can write the angular velocity of this ring about this axis is exactly same. So I can write angular velocity of ring about O prime, this is O prime, is also omega naught. From this diagram, this way, I hope you are able to imagine it, what exactly is happening here. So this ring's center is rotating in a circle about this, and its angular speed, it's not exactly symmetrical, it will be like this, and this even like smaller, it will be something like this diagram. This is the center of ring. This ring will be describing this circle, and its angular speed is given as omega naught about this axis, is it? And about which the finger is also rotating with same angular speed, omega naught. So about that axis, it's omega naught. Then I can write velocity of center of mass of ring is related in this manner. So by these two relations, I can get the relation between omega and omega naught. So you can write equation 1 and this is equation 2. Then from equation 1 and 2, we can get v equal to r minus small r into omega naught is also equal to omega into capital R. So omega relations we are getting, it's omega naught divided by capital R. Okay, so that is one relation we got. This now it is asking two questions. Let me read those questions. So first, it's mentioning the minimum value of omega naught below which the ring will drop down. So that is like you can just imagine, if you are just holding your finger at some angle and ring is just there without rotation, then definitely you will not be able to hold it actually, is it? So ring in this manner, it will not be, centripetal force will be like providing, and some friction will be there, so that things will be balancing. So if I draw the diagram, let's say this is the center of mass of the ring at some moment, then mg force is acting on it, and this is the point of contact. So here it's finger like this and the ring is touching in this manner, then normal reaction will be acting in this direction, and the friction force mu into n will be acting upward, resolving. If I take this angle as theta, then I can resolve into components. So n, it's n cos theta, and this is n sin theta. Friction force mu n cos theta, and its component of this friction force in this direction is mu n sin theta. Now I can balance the things actually for capital like ring. So for ring, so what we can write actually, mu n cos theta minus n sin theta must be balancing mg. Let me write, this is equation number 3, and here this net I can write mu n sin theta and plus n cos theta must be providing the required, that is m, about this point. You can see it's they must be providing the required centripetal force here. So that, okay, see here, so the angular velocity of this center of mass about this axis I already calculated, that is omega naught. Angular velocity of this about this axis omega naught, and this distance we can easily write, it's basically this is equal to capital R minus small r. Then this force completely actually like getting transferred to this ring, so I can write now this is the force which is providing the required centripetal force, so I can write this is equal to m into r minus small r times omega naught square, mr omega naught square. Just simply this is, let's say, equation number 4, then 4 by 3 I can write, and n will simply gets cancelled. This is mu sine theta plus cos theta divided by mu cos theta minus sine theta, and that can be written as r minus small r into omega naught square divided by g. Right, so now see here we will use some assumption because definitely this theta will be small, so for small value of angle theta we can write sine theta will be equal to what, almost 0. You can write sine theta almost 0 and cos theta will be 1. So if I am substituting it, then it will be 0 0, it's 1 and it's mu, so 1 by mu I got, and then rearranging it, this implies it's equal to 1 by mu omega naught g divided by this, and omega naught I am getting, that is equal to under root g divided by mu times capital R minus small r under root over this. So this is the angular speed at which the ring will be able to rotate without sliding or without falling down. So that is the question number 17. So we are getting the minimum angular speed is this at which like ring will be able to rotate. So minimum value of omega naught below which ring will drop down, will slide down, this is the minimum value. Right, next question, it's asking total kinetic energy of ring. Okay, now in that situation you must be remembering when total kinetic energy in combined rotational or even translational or like that motion, it's asked like it's always easier to go for instantaneous axis of rotation, because about that the combined motion is simply or purely rotational motion. Then we can simply write the total kinetic energy is equal to purely rotational kinetic energy. So in next question it's asking about the kinetic energy or total kinetic energy of ring. So 18, total kinetic energy of ring, right? So that I can write total kinetic energy is equal to what? This kinetic energy I can write, it's a rotational kinetic energy about instantaneous axis of rotation, and that is equal to half I this axis, is it, IAOR into its angular speed omega square. This is what, ring, so mr square plus by parallel axis theorem, so this will be 1 by 2 into 2mr square multiplied by omega, and omega we have already got the relation, substituting it there, so it's capital R minus small r whole square omega naught square divided by capital R square. This getting cancelled, 2 gets cancelled, then we are getting kinetic energy total is equal to m, this is r minus small r whole square into omega naught square. So this will be the kinetic energy or total kinetic energy of this ring, because we are calculating it about instantaneous axis of rotation, so it's taking care of everything translational, rotational, or like combined motion. So this is about that problem. I hope you understood. Let me still try. You are you should be in position to understand what exactly is happening, what is the practical situation. Ring is rotating like the finger, you are rotating like this, holding ring in this manner. So in this situation we can look at it from different point. If I just look at it about this axis, is it axis passing through this point, actually bottom of this your finger about which you are rotating, then this is simply straightforward, like is ring is finger is rotating in this manner, and on that finger ring is also there. So this is that point, and we know we are given about this the angular speed of finger is also omega naught. By just retracing its path, so center is rotating from here to there, and this point or your ring is moving from here to there, describing the circle, so it's moving from here to there. The theta described is same, that's why I can write the angular speed of finger is omega naught. Then I can write about this axis angular speed of center of mass of this ring will be also omega naught, and velocity of center of mass can be expressed this is the instantaneous axis of rotation, because it's clearly mentioned the point of finger in contact with the ring is doing without like rolling without slipping. So it's like for a moment it's in rest, and that we can say it's like instantaneous axis of rotation. Then about that we got one relation again for center of mass. So V is equal to R omega. By using these two relations, we are getting the relation between this omega. This omega is the angular velocity of this ring about instantaneous axis of rotation. So we got this relation. This is used here to calculate the kinetic energy easily. So we got this. Another thing here, if I am drawing it, so center of mass is rotating about this axis with angular speed omega naught. This distance is capital R minus small r. Now force balancing here, so you can understand normal friction will be acting in this direction, friction will be acting, so if finger is this way, this is the ring, then friction will be acting along this direction, and normal friction will be acting in this direction, normal. So this is normal, this is friction resolving into components, we are getting this relation, vertical balancing this, and then this complete force like horizontal force is providing the required centripetal force. Solving, we are getting this relation. Here we are using one like approximation, that is small theta, so sin theta is equal to 0 and cos theta is equal to 1. Substituting, we are getting the required corresponding minimum omega naught, so that like ring is not slipping down. So this is all about this problem. I hope you understood this. Let's clear your doubt. Thank you.